McTiny, fast high-confidence post-quantum key erasure for tiny network service, or how to fit an elephant into a matchbox.
There's a tension between what cryptographers want and what network people want. What cryptographers want is to protect us against future quantum computers. There are various proposals for doing this. In this talk, we're going to focus on one of these proposals, namely McEliece's code-based encryption system. Code-based doesn't mean it's software. Well, there is software. What it means is that it's based on the mathematical theory of error-correcting codes to encrypt your data. Now, when McEliece had his original crypto system, he said, here's a key size you can use for 2 to the 64 security. But even though that might have sounded reasonable in 1978, now lots of people can do 2 to the 64 operations. We've done 2 to the 64 operations. It's not that big a number. You need a higher security level. So how does McEliece's system scale up in security? Well, you can aim for any 2 to the lambda security, 2 to the 128, 2 to the 256. And how big are the keys in McEliece's system? Well, there's some scalability formula that says, here is how big the keys are. Here's how that scales up as lambda gets bigger and bigger. And that formula is shown on the slide. You might think, wait a minute, the security against whatever attack McEliece knew about, some attack from some algorithm from 1962, that was an algorithm that he knew in 1978. But attacks get better, right? So what's the security of the same system now? Well, the answer is that amazingly, if you take the same encryption system now and say, how big are the keys for 2 to the lambda security? What's that scalability formula? It is the same scalability formula, the same scaling of the keys relative to the security level. And now you're thinking, well, okay, that's because nobody's actually looked at the security of the system. Nobody's studied it, but that's not true. Here's a whole bunch of papers which have algorithms which all use that same amount of time to break the system. They all need the same, for the same key size, can provide 2 to the lambda security against all of these attacks. Some of these are looking at post-quantum security. Now, you know that quantum computers reduce the cost of searches, and all of these attacks are some huge search that you have to do for some secret. And when you have a quantum computer, you know that AES-128 with a 128-bit key, quantum computers, Grover's algorithm reduces the attack cost down to 2 to the 64. So you need to double your key size to compensate. Maybe quantum computers aren't that powerful. The quantum computers are going to have some overhead, so it's more expensive. But the point is that you have at least half your security level against quantum computers. And then the searches that you have to do, all of these algorithms have the same gigantic searches that you have to do. So you have the same security level. Here's a plot of how the security has degraded. Instead of saying how big do the keys need to be for a certain security level, you can say for a given big size of key, what is your security level? And here's the graph, no degradation at all. As this is a timeline of the attacks from 1978 to 2020, all the bullet items there are the different attack papers, and the security level has not changed. It might seem kind of pointless to draw a graph like this, but if you draw the same graph, for example, for lattices, then lattice-based encryption has this graph. If you go back just 10 years, then lattices were believed 10 years ago to have 42% more bits of security than people say lattices have now. And if you go back 20 years, people thought lattices had super exponentially more security than what they say lattices have now. So lattices are scary. McEliece's system, 40 years, has held up just fine. Concretely, what do the security levels look like and what do the parameters look like now? Well, there's this ongoing post-quantum cryptography standardization process, which has submissions, including Classic McEliece. Go to classic.mceleece.org and you can see these numbers for software that we took for this paper. And there's, on the slide, you can see performance numbers for low, medium, high security levels, like AES 128, 192, 256. In this talk, in this paper, we're looking at the high security level. So the rightmost column, McEliece 6960, 119, you can see the performance numbers there. Now, for a networking person looking at this, If the cryptographers are saying, well, you should be using this solid conservative system for high confidence in your post-quantum security, then there's obviously some key issues in these numbers. So what are the key issues? Well, there was one big issue really, which is the keys, the big 1 megabyte public keys. And now from a networking perspective, how big of a problem is that? Well, you connect to a server and you're going to be, say, downloading multiple web pages from the server, maybe doing some uploads, and a typical web page is multiple megabytes. And if setting up that connection costs you another megabyte, maybe that's okay. Maybe we have enough bandwidth that we can tolerate that. And also the cost of creating a key, that was the other big number, was it takes some significant fraction of a second to make a new key. And we want, like a client should make a new ephemeral key, send it to the server, and then the server encrypts a session key back to the client. And we want this happening frequently so that the client can forget the key later, and the server forgets the key. You throw away your secrets for key erasure, forward secrecy. If somebody steals the server later, they shouldn't be able to go back and decrypt data or steals the client. Is it okay for a browser before it sets up a connection to spend some fraction of a second doing some computation? Yeah, maybe it's okay. But there's a bigger problem, which is memory on the server. Imagine for the server, you have a client sending you 1 megabyte key. And once you've received the whole key, then you encrypt the session key, you would send that back, and all right, now everything flows smoothly. But at the same time that you're receiving that megabyte, you are having a whole bunch of other clients which are sending data. You've got half a megabyte from this client and 99% of a megabyte from this client. And you have to be storing all of those at the same time. Now, maybe you can handle all your legitimate traffic, but setting up for the 1 megabyte per client means an attacker looks at this and says, ooh, great, I'm going to start sending you 99% of a megabyte and then not finish it, and then another 90% of a megabyte at the same time. And you have to buffer all of this. It's not just the network traffic, it's your RAM getting flooded by the attacker. The point of this paper is to say, can we get rid of that storage on the server? Can we avoid having the server store any data per client and still encrypt to these 1 megabyte McEliece keys?
To see how, if this is possible, we have to look a little bit into how the system works. So first of all, what is this public key? Public key is a gigantic matrix, and the number across is almost 7,000 entries. Now these entries are just zeros and ones, so each entry is small, but there are a whole lot of them. There are 1,500 high and about 7,000 across. When you look at this, then on the left-hand side, you do see an identity matrix. So the first way we could save some time, transmission or space in the transmission, is to ignore this identity matrix, because everybody knows that there's a 1,500 by 1,500 identity matrix. And yes, of course, we're ignoring this. So the public key is basically just the remaining part, but that's still 5,400 across, 1,500 high, many bits, and that's where the 1 megabyte comes from. The way the encryption works is that you pick randomly and secretly a bunch of columns. So I've picked those blue columns up there, and then just for the example, let's assume they just hide 4. And then the encryption operation just adds up this 4 vectors. And everything is over F2 of the binary numbers. So when I'm adding 0 plus 1 plus 0 plus 1 in the top row, then I'm getting 2, which modulo 2 gives 0. And then the other entries are the same. Now that you understand how this works, one way of avoiding having to send the whole matrix at once is that we can spoon feed this public key 1 column at a time. So the client sits there and sends a column of the matrix, and the server includes it in the intermediate result or not. That still requires some storage per client. So the server still would need to keep this intermediate result on the server side. And so there's again an issue, a smaller one because it's only the height of the matrix, but there's still an issue that the server would allocate per client memory. So if you want to do this on the internet without any per client state, then can we do the same? Can we send the intermediate result back in a cookie or something? Let's assume we're sending back this intermediate result. And our attacker here is listening to everything. So the attacker sees something coming in, me replying. Something else coming in, me replying with the very same value. So he has just learned that I just ignored the column that came in, so that bit was 0. No, 0, not 1. So then that is not going to work. So if we reveal intermediate results, we have a problem there. That is the secret message, which we'll be giving away. However, this is still the basic idea of how to make this thing work. So in McTiny, we chunk up the key into nice packets that fit into network packets, including some header and cookie information. And then the client feeds the server these packets. The server does a partial operation on these such that the server can forget everything afterwards. Everything is sent back to the client in a cookie in a way that even our attacker cannot interfere from it, whether I have edited something or not. If eventually the server's long-term public key gets leaked, and that's the whole idea for having key erasure or forward secrecy, it is still secure. An attacker will even then not figure out what was sent. Now, there's a lot of stuff in the paper, so please go to the McTiny paper to read all of it, how it avoids replay attack and similar attacks. But the summary is that we managed to do a protocol which handles the big McEliece keys without any per-client state on the server.
And finally, all this is implemented. If you're interested in the software, then you can take a look at mctiny.org and measure it yourself and see the server's not allocating any memory. That's it. Thank you for your attention.